e to the x's and, and so forth. So let's go ahead and do this. So find the velocity at time t would be that derivative. So we won't go through the whole thing, but we'll go through some of it here. So y primes, again, good review for those of you still doing the gateway. It's just a quotient rule, right? So derivative of the top is 1, leave the bottom alone, minus the top left alone times the derivative of the bottom, right? Which would be 2t, all over the bottom square. Okay, so 1 plus t squared squared. So we want to combine up here. We have 1 plus t squared minus 2t squared. So that becomes, so y prime becomes 1 minus t squared over 1 plus t squared squared. Okay, now that's part A. So you will hear me a lot this year say, when is a fraction equal to 0? When is a fraction equal to 0? When the top is 0, right? A fraction is equal to 0, because that's what we're going to be doing, is doing the derivative set equals 0. A fraction is 0 when the top is 0, and the bottom is not, right? If the bottom is 0, then you have 0 divided by 0, but then we could probably be factoring and canceling something here, right? Which we can't right now. So all we have to worry about is the top, okay? Even if this was a calculator problem, you wouldn't have to set the whole thing equal to 0. You would only have to set the top equal to 0, right? Because that's when a fraction is 0, is when the top is 0. Well, that's going to be at plus or minus 1, okay? And we can ignore the negative because t has to be between 0 and 4, okay? So our number line, so our y prime number line is just going to have a 1 on it, and then we're going to put some numbers in. And so the bottom's always positive because it's squared. So you put a 0 in here, you get a positive. Put a 2 in here, you get negative. Okay, and so now you can go from there with that. And right, Sam, I'm assuming that was a question, pretty much was a derivative, right? Okay, so now, what is the acceleration? So y prime was 1 minus t squared all over 1 plus t squared squared, correct? That was y prime. So what's y double prime? Okay, so let's go through it. Now, again, it's a good practice for those of you still doing the game. So here at the top, negative 2t. Bottom left alone, 1 plus t squared squared. Minus top left alone, derivative of the bottom. Now, what's the derivative of the bottom going to be? Let's work on it over here. So I'm going to have 2 brought down in front. I'm going to have 1 plus t squared left alone to the first times the derivative of the inside. Okay, well that's 4t. I'm going to distribute that through there. So that'd be 4t plus 4t cubed. 4t plus 4t cubed. Now they do. Is that all right? Okay there? Okay. All right, so that's the derivative of the bottom over there. All over the bottom squared. So squared would be to the fourth, so 1 plus t squared to the fourth. Right, now I need, if I'm going to go here, when is it 0? So when is this 0? Is when the top is 0. Okay? So I'm going to need to solve that because now I have to do a number line, an acceleration number line to be able to do the bottom. So when is the top 0? So this is a FOIL. I need to combine these terms, right? Because again, this could be no calculator problem. All right, this could be a no calculator problem on the midterm. This could be a no calculator problem on our quiz next Wednesday, right? I'm not saying I'm going to get into that much algebra, but there's going to be some algebra on it next Wednesday. Okay, most of the quiz next Wednesday is no calculus. Okay, all right. So now we're going to get into limits today. So there's going to be some algebra to do with limits. If you remember, we had bow tie, we had that kind of stuff. So maybe some of that again. Okay, and then could be some algebra. There's going to be some that's simple algebra because I mostly want to quiz you on the calculus. Right? It's not an algebra quiz, but we got to be able to do the algebra too. All right, so this is going to be squared. So 1 plus t squared squared. That's going to be 1 plus 2t squared plus t to the fourth. Right? I just got to FOIL that. Okay, and then I have a negative 2t out in front of it. So I'm going to distribute that negative 2t to all that. So it's going to be negative 2t. That's going to be negative 4t cubed, and then negative 2t times that is negative 2t to the fifth. I think I got that. Okay, now I got a FOIL right here. Now I got a minus. Well, I'm not even going to put that minus yet. I can put that minus to wait on that. So now I got a FOIL right there. Okay, so let's FOIL that. That'd be 4t. Outers would be 4t cubed. Inners would be negative 4t cubed. That's nice. And last times last would be negative 4t to the fifth. Okay, now those are going to cancel right there. And then I've got this minus here that's got to distribute all that. So that's going to be a minus 4t, minus 4t, and that's going to be a plus 4t to the fifth. Okay, that's all the top. Now, to be honest, I don't really care what the bottom is. Okay, let's look at the bottom a minute. Number one, we care about when the top is 0, right? But there's my, well, I could simplify that. Let's simplify that a little bit. So find the acceleration at time t. So what can I put together? My fifths. Okay, I got 2t to the fifth. That's those. I got minus 4t cubed. I got minus 6t. Okay, all over 1 plus t squared. How am I doing so far? Did I make a mistake somewhere? I got this worked out somewhere. Double check. Okay. All right. Now, okay, once I get to this point, okay, now I want to know when that equals 0. So let's talk about the bottom for a minute. Okay, so I've got, will the bottom ever equal 0? I don't think it ever will, because what's the littlest t squared could ever be? Well, it could be, t squared could be 0, right? T squared could be 0, otherwise it's positive. So 0 plus 1, so the littlest this could ever be is 1, and then 1 to the 4th power, and that's always going to be positive. So that can't ever be 0 in there. So I know that'll never be 0. So now I'm just worried about the top. When does that equal 0? Well, I can take out a 2t, and that's going to give me t to the 4th minus what? 2t squared minus 3 equals 0. Is that right? Does that look good so far? Okay. And so what about this? Can that factor? So 2t equals 0, so that's going to be t equals 0. So that's one of my places. And then what about this? This would be t squared, 3 and 1, negative, positive, right? Okay, so is this ever going to equal 0 right here? T squared plus 1? T squared plus 1 is never going to equal 0, right? T squared is not going to be negative 1, right? So t squared minus 3 equals 0, so t squared equals 3, so t could be plus or minus square root of 3, and I can't have a negative, so square root of 3. Okay, so there we go. So again, probably more algebra than you have to worry about for the quiz next week, but definitely not more algebra than might be on a multiple choice thing, on a midterm, or on the AP test somewhere, or one of those kind of things. Okay, so there you go. So that's the second derivative. Now, there is some other things we could have done that maybe would have made that a little simpler. Might not have had to FOIL as much. Some of you probably see it. Right up here, I could have factored out a what? Right here, if I wouldn't have distributed this through here, right? Right here, I have a 4t and a 1 plus t squared. I could have taken out a 1 plus t squared there. Pulled that outside. That would have been this 1 plus t squared right here. And then I'd have had a little bit simpler stuff left, and I wouldn't have had to FOIL as much, right? Like I did all this stuff. So I could have taken out a 1 plus t squared up there, okay? And actually then canceled it with one of those, you know? So there's some things I could have done that might have made life a little easier there without doing as much FOIL, but, okay? All right, so anyway, when is it 0? So at those places, and then when's it speeding up, slowing down, then do your number line and go from there. Okay? All right. All right. So I tell you what, let's go ahead, because I want to give you some work time today, so let's go ahead and move along here. So go ahead and get your notes out. And so one of the things on the quiz next week is going to be those kind of questions with the chart, the first derivative, second derivative, and number lines and all that. Okay, particle motion. We'll review it again next Tuesday. Okay, and we'll do a few more of those problems on the paper there to work on. Okay, so what we want to do is go back and review what we did with limits. We did a pretty good job on this, actually. Last time we did this in chapter 2. So we're just going to add to it a little bit here, really. We're just going to add the concept of infinity and what happens when limits don't exist. We're going to rewatch those videos here just a little bit today. Okay, so I don't know how much of this you want to put in your notes, maybe the new stuff, maybe, right? I don't know that you have to do a lot of this. So this is what we were doing before, right? So limit of this function as x approaches -1. You're going to say what? What did we say? Does not exist. Now, here's what we're going to add to it a little bit. That was good enough on the last quiz. Now, I think on one of the worksheets we did last time, it did say, if the limit does not exist, discuss the one-sided limits, right? So what we're going to have to do on next week's quiz is if you have a does not exist, you're going to have to discuss why it does not exist, okay? And so we're going to be talking a lot today about the reasons why a limit doesn't exist. Now, we talked about the cars don't meet, right? So, but what I'm going to want you to say is, okay, x approaches -1 from the left equals, now we should say the limit, of f of x, but, okay, as x approaches -1 from the left is 2. And the limit as x approaches -1 from the right is 1. That's why the limit does not exist. So you're going to have to put that in. Okay, so on our next quiz, saying the limit does not exist is not enough to stop. You've got to then talk about why the limit does not exist. One of the reasons is the cars don't meet. The limit on the left is different than the limit on the right. Okay, what about the limit as x approaches 1? -2. The cars meet right down here, -2. The diner burned down, doesn't matter. Where do they meet? What are the y values getting close to? What are the y values approaching as x gets close to 1? The y values are getting close to -2, right? We don't care that the y value is different. Now, if I ask for f of 1, what would you say? F of 1 is what? -1, right? The function output at 1 is -1. So so if you were thinking does not exist, what you might be confusing that with is discontinuous. The function is not continuous at 1, right? Remember, we had 3 things had to happen for a function to be continuous. The limit had to exist. So right here, this function is not continuous here. There's a break, okay? Because the limit doesn't exist. Right here, this is discontinuous because the limit had to equal the actual output, right? The limit as x approached 1 had to equal f of 1. Okay, it doesn't. But there is a limit. Okay, the limit is -2. That's what the cars are approaching. But the function is discontinuous because the limit is not the same as the output. Okay? And then we had a third reason something was discontinuous, and that is the function has to have an output. It has to have an output. There can't be a hole or a vertical asymptote or something. So here, the function's discontinuous because the function's undefined at 3. There is no f of 3. Okay? But that's a different question than limits. Okay? Whether a function's continuous or not. All right, and then again, like I said, so what's the limit as x approaches 3? So the answer, what's the limit as x approaches 3? 1, right? 1. The limit is 1 because that's where the cars are meeting. That's what the y values are getting close to. Y values are approaching 1, okay? Even though there's a hole there, it doesn't matter. Okay, so the limit exists at those 2, but the function is discontinuous. So notice I picked the 3 places on this function where it was discontinuous. Okay, and then we discussed and talked about limits then. All right, so now let's talk about infinity. So you might want to draw this picture in your notes. It's up to you. But so now we're going to get into infinity. Well, infinity involves asymptotes, right? Infinity involves asymptotes. Now there's two different types of functions that deal with infinity. There's when the inputs are going towards infinity, and there's when the outputs are going towards infinity. Okay, those are two different questions. Okay, when the inputs are going towards infinity is what you see up on the top. Now that actually is that determines a horizontal asymptote. Now, sometimes people get confused about asymptotes. They're different. Vertical asymptotes we're usually pretty good at. Vertical asymptotes, when we're dividing by zero, it's undefined, right? There's no output there. We usually kind of get those. Horizontal asymptotes we have a little tougher time with. Horizontal asymptotes are when x is approaching infinity. End behavior, right? What's happening to the function way, 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 way out there, and what's happening to the function way, way, way over there to the left. That's what a horizontal asymptote is. Okay? It's a limit as x approaches positive or negative infinity. So on this graph, as x approaches positive infinity, the function values seem to be getting closer to what? 1. Remember, it is possible for a horizontal asymptote to be crossed. You can have a function come up and then come back down and then go like that, right? We don't care that it crosses it and it could cross it a bunch of times. We only care what are the y values doing. What we would do is if we wanted to look for a horizontal asymptote on our calculators, we would look at a table and we'd trace out at 1,000,000 or 1,000,000,000, right? Get on a table, get on a calculator table like we used to do, and put in 1,000,000 or 1,000,000,000 and look at what the y values are, right? And it'd be getting closer and closer to 2 or whatever this line is right here. Okay, so you can cross a horizontal asymptote. It's just what are the y values when you get way, 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 way out there. Okay, so this one looks like it's approaching 1, and then negative infinity would be way, way, way out here, and again, it looks like it's approaching 1. It wouldn't have to be the same. It could be different, right? But it looks like approaching 1. Okay? All right, this is an actual, this is an actual graph of something. This would be the graph of, I think this would be the graph of this right here. And we're going to talk about that in a little bit, okay? But what would you, algebraically, if you saw this, what would you do? You'd factor, right? You'd have x minus 1, then you'd have x plus 1, x minus 1, because we're going to do some with graphs, but most of our work is going to be with equations, right? That's what we're leading up to here. So what you would do is you'd factor out x minus 1, you cancel. Well, that's the whole. You just canceled out the whole. Remember we said one of the things we talked about the other day was 0 over 0 is a hole in the graph. So what happened is the 1, there's a hole, and at negative 1, you would get 1 over 0. And I don't know if you remember that, but we had talked about if you get a number over 0, we said just say does not exist. Well, if you get a number over 0, it does not exist because it's a vertical asymptote. That's what's happening. So right here we got a vertical asymptote at negative 1. Okay, so that's where this graph, if you graph this on your calculator, this is what it would look like. Okay? All right. Now, actually, if I put a 0 in here, I'm not sure it would look quite like this. I think it would be off a little bit because if you put a 0 in here, you get negative 1 over negative 1, which should be 1. You don't get 0, 0. So it wouldn't look exactly like this, but it'd be very similar. Okay, Anyway, that's beside the point. We'll get into that a little bit. Okay, what's the limit then as x approaches negative 1? What would you say? Does not exist. Right? Now, okay, and then remember we said that's not enough now, so we're going to go on to that. But listen, remember, for a limit to exist, the cars have to meet. End of story. For the limit to exist, the cars have to meet. I mean, that's just it. And clearly at negative 1, the cars don't meet. Okay? So for the limit to exist, the cars have to meet. And where they meet is the limit. So the answer to a limit is always a number. Infinity can't be an answer to a limit. Now, we're going to fudge that a little bit. If we get infinity as an answer, it does not exist, and then infinity. and we'll talk about that, okay? But if a limit exists, it's a number, it's where the cars meet. These cars do not meet at -1, so the limit doesn't exist, but we got to do more than that, right? So we got to talk about the one-side limit. So what's -1 from the left? Where's the car on the left going? The car on the left is going to infinity. Where's the car on the right going? -infinity. So if the cars don't meet, we got to talk about the left car and the right car, where they're going, okay, and why they're not meeting, okay? That's basically it. Either the cars are going to meet, the cars are not going to meet. If the cars don't meet, we got to talk about where the left car is going, where the right car is going. That's basically it. Okay, what's the limit as x approaches 1? 1/2, right? This hole is right here at 1/2. The cars are meeting at 1/2. Cars are meeting at 1/2, so that's the limit. Okay? All right. So, here's another one. Another typical is kind of a graph looking thing. Okay? What's the limit as x approaches 3? Does not exist. Cars don't meet. Now some people might say, hey, both cars are going to infinity, but infinity is not a number. They're not going to meet. They might be driving side by side, right? But they're not meeting. Okay? So what do we say? We say x approaches 3 from the left equals infinity. X approaches 3 from the right, also infinity. Now I'd probably let you get by with this one and just say x approaches 3. I would probably let you get by with this one and say does not exist, infinity. Because both are going to infinity. So if you say does not exist, infinity, I think if you type this one into your calculator, if I gave you this equation, you type in your calculator, I think your calculator would say infinity. It doesn't say it does not exist usually, which I don't like. I wish it did, because technically that's not true. Okay, infinity is not a number. Infinity is not a number. And the answer to a limit is a number. Okay? So technically, if it's infinity, it does not exist. Okay? But I think it's good to just show left and right. Okay? In case one's positive infinity, one's negative infinity, then you got to say it separately. Okay, what's the limit on this as x approaches negative infinity? 2. As x goes way, way out here to the left, this graph seems to be going down to 2. What about x approaches positive infinity? 2. Simple, right? Y values are getting closer and closer to. Those are horizontal asymptotes. X approaching infinity is horizontal asymptotes. Okay, let's look at this little picture here. This is called, the red here is called a slant asymptote or an oblique asymptote. Okay, a slant asymptote or an oblique asymptote. Okay, so this graph is going up here like so. Okay, all right. This would be something like, well, it doesn't matter. So what's the limit as x approaches 0? Does not exist. As the cars come in here towards 0, the car on the left is going, to infinity. Car on the right, to the right of 0, going to negative infinity. Okay? So that's what we would say. So the limit does not exist, the cars don't meet. We got that. What is the limit as x approaches infinity? What are the outputs? Where are the outputs going as x goes way, way out to the right? Well, yeah, but it's what number is it approaching? Wait, I just said infinity is not known. Infinity, right? They're just getting bigger and bigger and bigger. As x goes way out here, the outputs are just getting bigger and bigger and bigger and bigger and bigger, right? So what's the answer? Does not exist, because it's got to approach a number. And then you would say infinity, right? Infinity. Okay? Remember, anytime you say does not exist, you got to tell why. Why doesn't this exist? Because the outputs are going to infinity. Okay? The outputs are going to infinity. I mean, a simple example would be x squared. Y equals x squared. What's the limit as x goes to infinity? Infinity. You put in bigger and bigger numbers, you get out bigger and bigger numbers. Right? Okay? How about negative infinity? When you go out to negative infinity, what are the outputs doing? They're going to negative infinity. So we say does not exist, negative infinity. Okay? The outputs are going So sometimes you don't get a horizontal asymptote is what I'm saying, right? So sometimes as x goes to infinity, when you go way, way over here to the right, or you go way, way over here to the left, the graph's just going up, just blowing up, going way, way up or way, way down. It's not approaching anything, right? So sometimes there is no horizontal asymptote, so you just get that. All right, so the stuff in the red is the stuff we had done before, okay? So the stuff in the red is what we had done before. The limit as x approaches a, okay? You're either going to get a number. So if we have an equation, what are we going to do first? We're going to do direct substitution. We're going to plug in a 2. We're going to plug in a 3, right? Direct substitution. So we're going to plug in, we get a number, boom, we're done. The limit exists. Or we might get 0 over 0. Remember we said keep going. So what's keep going mean? You might be able to factor. You might be able to get a least common denominator, bow tie. You might multiply by the conjugate, right? So we'll practice some of that. And then something may cancel, and then you can plug in and get your answer. So we're still going to have some of those on the quiz, right? The same thing we did back in chapter 2. So you maybe can get out the old worksheets you had. You know, we'll do some other practice, but get out the old worksheets you had. You might be able to do some of those. Okay? I think there's some IXL ones too, maybe. I'll look that up. And then the other thing we said that might happen is you might get 3 over 0, 2 over 0, something like that. Now, last quiz we just say, if you get that, just say does not exist. Okay? If you get 7 over 0, 3 over 0, just say it does not exist. Now, so what have we added? We've said, well, you can't stop now when you get does not exist. So, one thing we've added in the blue here is if you get 3 over 0, 4 over 0, 5 over 0, you say does not exist, and then you have to say why. Typically, that means look on the left and the right. Okay? As x approaches 5, we would say, okay, let's look at 5 from the left, let's look at 5 from the right. Typically, what's going to be is you're either going to get positive or negative infinity, right? If you get something over 0, if you get 6 over 0, 5 over 0, that is a vertical asymptote. Every time. Every time. So what's going to happen in a vertical asymptote? It's going to go up, it's going to go way down. Right? It's going to be positive or negative infinity. That's all you got to figure out. Okay, and we're going to do one and show how you can figure it out. It's easy to see when you're looking at a graph. It's easy to see. But if you're looking at an equation, how do you tell if it's positive or negative? Okay, that's what we're going to talk about. All right. And then the other new thing is instead of doing the limit as x approaches 2 or 3 or 1, what happens when you have x approaches infinity? Well, those are horizontal asymptotes. That's what I just got in showing you. So if you've got x approaches infinity or negative infinity, you're either going to get a number, so it's coming down and it's approaching 2, right? Way out here, it's approaching 2. Or you're just going to get, it's just going to go up. It's just going to go up forever or down forever. And so you're going to get does not exist. Those are the two possibilities. So there it is. That sums up the things that can happen, right? Okay. All right. So, let's see what that looks like with some equations. Okay? See what this looks like with some equations. All right, so on the first one, you're going to start out by doing what? Plugging in a 3, direct substitution. So we plug in a 3 and we get 11 over 0, which does not exist. It's a but it's going to be a vertical asymptote. Okay? It's going to be a vertical asymptote. Now, again, why is it a vertical asymptote? We're going to see this here in a minute. It's not really technically 11 over 0 because x is just approaching 3, right? X is just getting close to 3. So what happens to x minus 3 when x gets really close to 3? It's really small. It's like 3.000001 minus 3. Or 2.999999 minus 3, right? It's just a really small number. Well, what happens when you take, and technically, the top's not getting exactly 3 either. So what happens when you take 2 times really close to 3, you get really close to 6. And if you take really close to 6 plus 5, you get really close to 11. But actually, that part doesn't matter. Really close to 11, we don't, so what I often think about this is, I a lot of times will write this. What we got is 11 divided by something really small. Well, what happens when you take 11 divided by something really small? You get something really big. It depends how small it was. If it was 1,000,000, you get 11. If it was 1,000,000th, you get 11 million. If it was 1,000,000,000th, you get 11 billion, right? So what we have here is not really 11 divided by 0. What we have is 11 divided by something really small. And that's why we get something really big. And that's why it's vertical oscilloscope. That's why it's big. Okay, that's what's going on. All right, so now what you have to do is you have to say, okay, x approaching 3 from the left and x approaching 3 from the right. So here you have to do some little bit of calculation in your head. Okay, so you're going to do it this way. You're going to say, okay, x approaching 3 from the left would be like 2.999, right? So now, I'm going to take 2.999 and I'm going to put it in on top. Well, that's going to be 11. I'm not going to worry about that, right? It doesn't matter. Just put a 3 at the top, that's fine. The bottom, it matters. So what's 2.9999 minus 3? Small negative, right? Small negative. So, what's 11 divided by a really small negative? Big negative, right? 11. Now, if that would have been negative 11 on top, see, then we would have gotten a positive, right? We'd have negative divided by negative. So this is how you're going to tell if it's positive or negative infinity. You're going to have to make this little calculation. It's not much of a calculation. It's pretty easy. So I usually just write it out just like that. I think that makes sense. Okay, now what about 3 from the right? That'd be 3.001, right? Maybe I should even write that down here. 2.999. 3 from the right is 3.001, right? Well, what if I get 3.001 minus 3? That's a small positive. So what I got is 11 over a small positive. What's 11 divided by a small positive? A big positive, right? So there we go. So does not exist, and then I got to have this. So over here we were showing that. We were saying, okay, you gotta show the left and the right. Well, on a graph it's easy. Left goes to infinity, right goes to infinity, right? They might both be positive infinity. But here's how you do it with an equation. You would literally pick a number just to the right of 3, and you would pick a number just to the left of 3, and you would put it in, and that's what's going to happen every single time. Every single time. So it's pretty easy to calculate. Okay? All right. Now, let's talk about the other scenario we have, and that is our new one where x is approaching infinity. How are we going to deal with that? Well, here you just have to think big number. What happens if you plug in a big number? Okay, so this is where we got to talk about infinity. Now we're going to talk about some more on Monday. But if I plug in infinity, remember infinity is not a number, so plug in infinity. What do you get on top? You get infinity, right? Big number. What about the bottom? Still a big number. You get infinity over infinity. What's that? Go ahead and say it. I know what you're thinking. You think it's 1. It's not 1. Infinity over infinity is not 1. It might be 1. But it might be anything. Infinity is not a number. There's different sizes of infinity. Because, so think about it this way. Okay, if I plug a really big number in here, let's plug in 1 billion. What happens with a 2? 2 billion. Plus 5. Now how much does that 5 matter when it comes to 2 billion? I'm Warren Buffett. I'm walking down the street. There's a $5 bill blowing around. Am I chasing it down? Am I picking it up? Well, he might. Maybe that's how he got to be a billionaire, because he chased down $5 bills. But you know what I mean, right? It doesn't matter. It's insignificant. The bigger the x gets, the less important the 5 is. Now, what about the 2? Is it important? Absolutely. You take 1 billion and double it, that's a big deal. So as x gets really big, the 5 becomes insignificant. What about the bottom? You got 1 billion, you lose $3? Big deal. The answer to that's going to be 2. If you graph that, you will see a horizontal asymptote of 2. Okay? The x's cancel. The 5 and the 3 are insignificant as x gets very large. Okay? As x gets very large, The 5 and the 3 are insignificant. This basically becomes 2 billion over a billion or 2 trillion over a trillion, and it's getting closer and closer to 2. Now, it's always going to be just a little bigger than 2 because this has a plus 5 and this is a little less than a billion, so it's going to be a little bigger than 2. So it's going to be above. It's going to be a horizontal asymptote coming from above. Okay? All right, what about negative infinity? That doesn't matter because it's still, as x gets really big negatively, the 5 still doesn't matter. Negative 2 billion, the 5 still doesn't matter. The 3 still doesn't matter. And so this still reduces to 2 because you'd have a negative divided by negative. And so it's still going to be 2. So one way to do x approaches infinity is just to think to yourself, what is going to happen as x gets really, really big? And there are certain parts of the equation that may not even matter. Okay? But these we do have to just kind of think through and think what happens in certain equations as they get real big. Okay, I want to watch just one of the video, a new video here, and we'll...
In this section, we'll delve into the mysterious and ancient relationship that exists between limits and infinity. As you calculate various values of f and evaluate different functions, you can come across some bizarre things. For example, take a look at this function. F of x equals the fraction 2x plus 1 divided by the quantity x minus 3. Now, if you plug in 3 to this, you're going to get 7 divided by 0. Now, I know we've seen 0 divided by 0 in a lot of previous examples, but we've never seen a non-zero number divided by 0. Well, that's bizarre, I know, and it indicates something important. In fact, whenever you substitute a number into a function and get a non-zero number divided by 0, it indicates the presence of a vertical asymptote. And this holds true for this function. Let's take a look at the graph of f at x equals 3. Well, remember, an asymptote is a line which a function cannot reach. Here we have an asymptote at x equals 3 because when we plugged 3 into f, we got a constant divided by 0. Now, by examining the graph of f, we can see that the limits as x approaches 3 from the left and right are different. As you approach 3 from the right, f gets infinitely large, so we can say that the limit as x approaches 3 from the right of f of x is infinity. However, as you approach 3 from the left, f of x gets infinitely negative, so we say that the limit as x approaches 3 from the left of f of x is negative infinity. Vertical asymptotes aren't the only asymptotes which relate to infinity. Horizontal asymptotes do as well, just in a slightly different way. To see this, let's look at the graph of f again. Now, as x gets infinitely large, or as we go along the x-axis, note that the graph of f is bending slowly downwards towards a height of 2. Now, if a graphical argument is not enough for you, take a look at this chart based on the function values of f.
This is what I'm talking about. Look,
as x gets larger, f gets closer to 2. Now, mathematically, this means that the limit as x approaches infinity of f equals 2. By the way, the limit as x approaches negative infinity of f also equals 2. As we travel left along the x-axis, the function approaches the same height. When I was explaining the last example, I said that x was getting infinitely large, and we translated that mathematically as the limit as x approaches infinity. Now, this type of limit is called a limit at infinity. If this limit exists for a function, then that function possesses a horizontal asymptote at the height given by the limit. Now, that's a lot of gobbledygook, but it's very simple in practice. Limits at infinity are very easy to calculate. All you have to do is compare the degrees in the numerator and denominator of the given function. By the way, the degree is the highest exponent. So if we take a look at f again, we'll notice that the highest degree in both the numerator and denominator is 1. Because remember, if we don't write a power, it's inferred to be 1. Now, in this case, the degrees of both the top and the bottom of the fraction are equal, and therefore the limit at infinity of this fraction is going to simply be the coefficients attached to those highest degrees. Again, sounds like a lot of gobbledygook. We just take the coefficients of those x terms to make up the limit. Therefore, the limit will be 2 over 1, and we say that the limit as x approaches infinity of 2x plus 1 divided by x minus 3 is 2. And remember, we already know from the graph of f that the horizontal asymptote is 2, so it checks out. Now, what happens if these degrees are unequal on the top and bottom of the fraction? Well, if the denominator's degree is higher, then the limit is 0. But if the numerator's degree is higher, the limit doesn't exist because it's infinity.
Okay, so he just said a lot right there. So we'll break that down. So this only works if we have a polynomial on top of a polynomial. Okay, so then we're talking about degrees, but we're going to get into other types of functions too, so we got to think about those. But basically, think about it. If the degrees are the same, then what's happening, so if they're both x squared, the highest power is both x squared. They're growing at basically the same rate, the top and the bottom, just depending on what the coefficient is in front. So if a 2 on top and a 1 on the bottom, the top's twice as big. If it's a 1 on top and a 2 on the bottom, then it's half, right? And so then it's just those coefficients of the high power. I call that high powers dominate. If you have x squared plus x plus 3 and x gets really big, a billion squared is way bigger than a billion, right? I mean, it's hard to imagine a billion not mattering, but if you had a billion squared, then literally a billion would be like nothing. That would be like a dollar would be to a billion, right? A billion squared compared to a billion would be like comparing a billion to a dollar, okay? It wouldn't matter. It would be insignificant. And a billion isn't a very big number. A billion has how many zeros? 9. A million is 6. A billion is 9. A billion only has 9 zeros. A billion is not a very big number, okay? So if you had a trillion squared compared to a trillion, you know, again, insignificant. So the high powers dominate. Now, if the numerator degree is higher, doesn't it make sense that that's just going to get bigger and bigger and bigger and bigger? And pretty soon it's going to be so much bigger than the bottom that you got this huge number divided by an insignificant number, you're going to have a big number. When the top is really big on a fraction, the number gets bigger. So that's going to infinity. But we would say does not exist in an infinity. And if the degree is higher on the bottom, that makes sense. The bottom's going to get bigger and bigger and bigger. What we just say, when you have a fraction and the bottom gets really big, what happens to the fraction? Gets really small. If you have a fraction where the bottom gets way bigger than the top, then that fraction gets really small because you're dividing by a big, big number. And so it's going towards 0. Okay? So that's what they're getting at right there.
In conclusion, if the limit as x approaches c of f of x is infinity or negative infinity, then f has a vertical asymptote at x equals c. Whereas, if the limit as x approaches infinity of f of x equals d, then f has a horizontal asymptote at y equals d. One word of caution. When we say that a limit equals infinity, we're actually saying that that limit technically does not exist, because limits have to be a real number. Therefore, it might be more enlightening to say that the limit does not exist because it increases infinitely, rather than saying that the limit equals infinity.
Okay? All right. So, let's take a look at this. Maybe jot this down now. Here's 3 problems here where we have this exact scenario. Okay? So, if we have polynomials, and we're talking about x going to infinity. We're talking about x getting very, very large, right? As x gets very, very large, either large positive or large negative. I'm gonna call negative infinity large. Okay, I understand it's really small, but you know, negative infinity we're gonna think of as a large number. Okay, a large negative. So what happens in one like this? You essentially ignore everything but the high powers. And that is going to be a horizontal asymptote at 1/2. Because a billion cubed is so much bigger than a billion squared, and really that's probably not the best example, because a billion isn't that big a number, we got to understand. Okay? It's more like a trillion or way more than that, right? What's a Google? 100 zeros. Googol. Google. Search engine. Okay? Google is 100 zeros. What's a Googleplex? I mean, a Google of zeros, right? Google to the Google power. It's a Google of zeros, which is just astronaut. I mean, it's just unfathomable how big it is. I mean, Google itself is hard to fathom. 100 zeros. Okay. But anyway, So a billion, 9 zeros, 12 zeros is not very big. Okay? All right. But every time you add zeros, it's amazing how much bigger it gets. Even to try to fathom, I always do this example with my Algebra 1B kids to get them to understand the idea of a big number. Well, I'll say if you had $1 million and you were going to spend $1 every second, how long would it last? In other words, how long is 1,000,000 seconds, right? And 1,000,000 seconds comes out to be like 11 days, I think. Okay, and then you'd be gone in 11 days. So 1,000,000 seconds is 11 days. Add 3 more zeros, go to 1,000,000,000. Well, what does that do? That's 11,000 days, right? Well, what's 11,000 days? I think it's like 30 some years. So all of a sudden you go from 1,000,000, that money would last you. So $1 million, you spend $1 every second, it would last you 11 days. If you got $1 billion, you could spend at that rate, and it would last you 31 years. I mean, that's pretty amazing right there, right? You add 3 more zeros, now it's how long? Now, if you had $1 trillion, well, we just said it was 31 years, so what would it be? 31,000 years. 31,000 years, okay? So compare 1,000,000, 6 zeros, to 1,000,000,000, 12 zeros. Not a whole lot more zeros. We just went from 11 days to spend that money to 31,000 years, right? I mean, so large numbers are hard to get our head around. So when I say $1 billion squared or $1 trillion squared, so we talk about you cube $1 billion, that's way bigger than $1 billion squared. Okay? And so these don't matter. When x gets really large, these are just going to kind of disappear. They're just not going to have an effect on this number. And so we end up with this. Well, the same thing happens here. You're going to essentially have, I like to call this high powers dominate. Okay, so this is going to end up being 3x over 4. Well, what happens when x goes to infinity? What happens to this when x gets really, really big? What's going to happen? That x on top is getting really, really big. So what's this number doing? Getting really, really big. So we say this limit does not exist. It's going to infinity. Right? So the highest power is on top. It's going to infinity. And then likewise here, as x goes to infinity, the only thing that really matters is the high powers. So the 2x squared and the 3x cubed, that's going to reduce down to that. So what's going to happen to that as x gets really, really big? Bottom gets really, really big. What happens to the fraction? Gets really, really small. Goes down to 0. Okay? So 2 over 3 billion, 0.0000000, right? It's going towards 0. Okay? So there you go. So even powers, okay, high power on top, going to be infinity, high power on the bottom, going to 0. All right. Now, what happens when you get one like this, where it's not about the powers? Okay, so let's talk through this real quick. Okay, let's talk through this real quick. So, now you just have to think about what happens to this type of function when x gets really big. So if I was working this problem, okay, I would probably look at it, I would probably split that one apart. Okay, well, I might even split it apart. It would probably be easiest to split it apart, so let's do that. Let's go ahead and do that. Maybe a lot of you would think to do that. So let's split this apart. Okay, so on some of these, we're just going to have to think our way through it. Okay, some of them are not as easy as those ones with just the powers. Okay, now what happens on that first fraction? Cancel, and we get 1/4. Now what happens here? I can flip that to the bottom, and that would be 1 over 4e to the 4x. I can add the powers. Now what's happening to that? Remember, as x goes to infinity. As x gets really big, what's happening to e to the 4 billion? This bottom's getting really big, so this fraction's going to what? 0. So this whole fraction here is just going to 0. So the answer on this one is 1/4. Okay? Now, the other way I could have done it, if I do this in red, I could have just wrote this as e to the 3x minus 1 over e to the x, and I could have just done this. I could have said, okay, as x gets really big, whoops, I thought I was doing this in red. Okay, this in red here, 1 over e to the x. Now, as x gets really big, what's e to the x do? Gets really big. So what's 1 over really big? Really small. So this just goes to 0 right here. So now I end up with e to the 3x over 4e to the 3x, and now cancel, and I get 1/4, right? So I could have done that too. Okay, so you just have to think your way through it. You have to say, what happens as x gets really big? Okay, let's talk about this. What happens to sine as x gets really big? Way out here, what's sine doing? Just bouncing back and forth, right? It's just bouncing back and forth, negative 1 to 1, right? What's the bottom doing? What's the bottom doing as x gets really big? Getting really big. What happens when you have a number that's negative 1 to 1 divided by a really, really big number? It's getting small, getting closer to 0. This would be a graph that I was talking to you about that goes like this. Right? Just keeps bouncing back and forth from positive to negative, but it keeps getting smaller and smaller and smaller and smaller and smaller. That's a horizontal asymptote at 0. Okay? So the limit is 0. Okay? All right? Let's look at this one. Okay, this is just, I'm actually going backwards now and reviewing back to kind of the beginning, stuff we've done in the past. Okay, so what would you do first? Plug in a 2, right? What do you get? 0 over 0. What's that tell you to do? Keep going. So x minus 2, x plus 2, x minus 2. Cancel the x minus 2. Now plug in your 2. What do you get? 1/4. There's our limit. That's a hole. There's a hole in that graph, and the cars meet at 1/4. Okay, that's what's going on. Okay, now what about this one down here? Plug in a negative 2, right? What do you get? What's your phone doing? What do you get? Negative 4 over 0. What's that tell you? Right away, we write does not exist, but we know we got to do more. So what are we going to do? X approaches negative 2 from the left. X approaches negative 2 from the right. So negative 2 from the left. We got to think about this. It's negative. What's to the left of negative 2? No, that's to the right. What's to the left of negative 2? Negative 2.001, right? Negative 2.001. Negative 2.001, let's plug it in here. Now, if we put negative 2 minus 2, that's negative 4. So the top, I don't care about it. The top's going to be negative 4. Doesn't matter. Okay? But now on the bottom, if I take negative 2.001 and I square it, what does that give me? Like positive 4.01. Something a little bigger than 4. So I get something a little bigger than 4 minus 4. So what do I get? A small positive. What's negative 4 divided by a small positive? Negative infinity. Okay? What about negative 2 from the right? Negative 1.99999. Again, I get negative 4 on top. That's not changing. But the bottom's what I care about. What's negative 1.999 squared? 3.99999, right? Positive. 3.999 minus 4? Small negative. Small negative. Negative 4 divided by a small negative? Positive infinity. Okay, so get something like this. It does not exist. We check the left and the right. There you go. Okay? All right. You don't have to write this. I'll probably come back to this on Monday, so I'm just going to, so you don't need to write this down right now. But just understand, in your book, they talk about infinity, using infinity like a number, treating infinity like a number, even though it's not a number. So sometimes we do that, okay, as kind of a shortcut notation. So if I see 1 divided by infinity, I think right away that that is what? 1 divided by infinity. That's 0. Okay? But what we really mean is 1 divided by a really, really big number is getting closer and closer to 0. But 1 divided by infinity, we would call it 0. Or 4 divided by infinity or whatever. Okay? All right, 3 times infinity. Right? It's infinity. We're going to talk a lot about infinity on Monday, about different sizes of infinity, right? If you have infinity and you add 1, it's still infinity, right? So I mean, so it's kind of interesting. 3 times infinity. Now, here's where it'll get really interesting, and I'm not even going to cloud your mind with this today. But the question we're going to come up with tomorrow is, well, just like infinity divided by infinity, if you guys wanted to say 1. Infinity divided by infinity could be 2, or 3, or 1/2. Or it could be infinity, or it could be 0, right? Infinity over infinity, we don't really know what it is. It's like 0 over 0. It's indeterminate, right? It might be something else. Really, infinity is just like 0 over 0. 0 over 0 is really something small divided by something else small. And infinity over infinity is something big divided by something else big. How's that work out? Well, 0 times infinity is the same thing. It's like 0 times, right? If you multiply by a big number, it's supposed to make it bigger, right? But if you multiply by a small number, it makes it smaller. What happens if you take a number that's getting smaller times a number that's getting bigger, and you multiply? Right? You want to say 0 there, don't you? Right? You want to say 0 times infinity is 0. It turns out sometimes it's infinity. Sometimes it's 0. Sometimes it's 2. Sometimes it's 4. Okay? Because what you have going on is you have a battle. You have this thing getting small times this thing getting big, and you multiply them, and they're battling it out. It's like, who wins? Is the thing getting small win, or the thing getting big win, or is it kind of a toss-up? Okay, that's what's going on. Okay, guess what's going to determine who wins? How fast the one getting big is getting big compared to the one getting small. Rate of change. Oh, what's rate of change? What's slower? The derivative. The derivative. The derivative is going to tell us how to do it. Okay? All right. Homework. Okay? Might as well pass these out now. Okay? Sorry, I meant to give you a little more. Hopefully. Not too big a homework assignment. Work on those. Now, I would still leave those other particle motion problems that I told you not to do. I would leave those, and we can do those on Tuesday. So just this really for Monday and practice for the gateway test if you have that. So this is like the 3rd line down, I think. This is the 3rd line down is what this assignment is on here.